Alright, so we're going to learn about probability distributions in Chapter 4, specifically discrete probability distributions. So the first thing I want to talk about is what is a discrete probability distribution and how is that different from a continuous probability distribution. And then we'll talk about how to create a discrete probability distribution. So the first thing we need to talk about actually is a random variable. And a random variable is a variable that represents a numerical value associated with each outcome of a probability experiment. And because a random variable is random, a value is associated with it that is random, and therefore it's not treated like a variable that you're used to, like in algebra. And for example, properties like x plus x do not equal 2x. And that's because, and the simplest way I can describe this is, let's say you're rolling a die. Okay, if you're rolling a die and x represents the number on the die roll, so it's a number between an integer, actually between 1 and 6. The first x might be a number between 1 and 6, let's say it's 2, but the next time you roll the die, it does not have to be the same number, right? It could be 3 or 4, and so it doesn't necessarily equal that number, the first number you got doubled, or 2 times that amount. So random variables are treated differently for that reason. And a random variable is discrete if all of the outcomes can be listed and if you can count the outcomes. And a random variable is continuous if you cannot count the outcomes. That's the word continuous, if you can't read that. So for example, if you have a discrete random variable on a number line, you can count all of them. So I can count the points on a number line. But a continuous random variable, still have our number line, but it's going to be a range of values on the number line, not just distinct points. So there's a couple ways and tricks you can use to kind of figure out if something's discrete or continuous. For example, let's go to the first one, the number of sales calls. Well, the number of sales calls, if I make a sales call, I either make the call or I don't. I can count the number of sales calls I've made, therefore that is discrete. Whereas the number of hours spent on sales calls, well, you can't really count that because time is continuous. Because if I have the number of hours spent on sales calls, I could perhaps have like a half an hour or 15 minutes, right? There's a bunch of different values. It could be any value on an interval. So that is continuous. And here's a good tip. If you can measure something a bunch of different ways, it is most likely going to be continuous. So for example, like sales, the number of sales calls, I'm just counting how many sales calls, so it's discrete. But as hours or time, you can measure that a bunch of different ways. I can measure how long I've been on a sales call in minutes and seconds, right? There's a bunch of different ways to measure it. So try to look through the next few and see if you can identify those as discrete or continuous. So you should have paused the video and tried to go through these next few. So the number of stocks in the Dow Jones Industrial Average, that's discrete because either the stock is there or it's not. By the way, that's the top 30 stocks in the US. That's what the Dow Jones is. If you've ever been curious to see, reading the news of, the Dow goes up and down. Discrete, there's actually 30 discrete stocks in the Dow Jones. The volume of water in a bucket, that is continuous because it is, it's on an interval, right? And you can measure it in a bunch of different ways. You can measure it in gallons and liters, quarts, milliliters, ounces. There's a bunch of different ways to measure volume of water. The height of a skyscraper is continuous. Once again, you can measure that a bunch of different ways. You can measure that in inches, feet. And the number of windows in a skyscraper is discrete because you're just counting the number of windows, right? You can't have half a window. The window's there or it's not. You count it or you don't. So that's the difference between discrete and continuous random variables. Now, because you can count the number of ways something can happen in a discrete random variable, we can come up with something called discrete probability distributions. And continuous probability distributions do exist. We'll actually talk about one in Chapter 5 called the normal distribution or a normal distribution. But a discrete random variable is easier to talk about, especially if you haven't taken calculus before. Continuous random variables, to talk about more in depth, usually require a more in-depth knowledge of calculus. So discrete probability distributions lists each possible value the random variable can assume together with its probability. And a probability distribution must satisfy the following conditions. So the first condition you should be familiar with, and that is a probability has to be between 0 and 1, including 0 or 1. But the second condition is probably new to you, and that is if you add all of the probabilities together, you get 1. So every time you add all their probabilities together, you get 1. So let's create a probability distribution using the next one, and we'll see that it uses both of these properties in this example. So we have an industrial psychologist administered a personality inventory test for passive-aggressive traits to 150 employees. Individuals were given a score from 1 to 5, where 1 was extremely passive, 5 extremely aggressive. A score of 3 indicated neither trait. The results are shown below. So we have the score and the frequency, and if I have a probability distribution, I list the random variable x, which is the score, and the probability of getting that score. So my random variable x is the same thing as the score, which is 1 through 5. But the frequency is how many people got that score. But now I want the probability. So if I want to get the probability, for example, of selecting someone with a score of 1 from this group, well, I know 24 people got that score. And if I add all these together, in fact, they tell me there's 150 employees, I get 150, and 24 divided by 150 is 0.16. And we can do this for all of them. So 33 divided by 150 is 0.22. 42 divided by 150 is 0.28. 30 divided by 150 is 0.2, and 21 divided by 150 is 0.14. So all of these probabilities, notice, are between 0 and 1, which is all probabilities should be. And on top of that, all those probabilities add to get 1. Okay, so that is a probability distribution for the industrial psychologist. All right, so try to do this next page on your own, and I'll complete it relatively quickly, but just try to do this on your own. Come up with the probability distribution, and then on the bottom there's 3 different charts I give, and identify which ones of these charts are probability distributions and which ones are not probability distributions. So the first one, you should have seen that there are 100 days total. It tells you in the problem, but you can also add them all up. And x represents the number of days. Oh, I guess we started at 0, didn't we? And so we take each number of days and we divide by 100. So this is just 0.16 divided by 100 is easy, which is pretty nice. And remember to double check that you got a all the probabilities correct. You can just add all those probabilities together and they should add up to 1, right? Which brings us to the next part. So there are a few charts down here, and we're going to decide if each of these are probability distributions. So the first one, days of rain and the probability of rain, is yes. That is a probability distribution because all of those probabilities add up to 1, and all those probabilities are between 0 and 1. Now the second chart on the right side is not a probability distribution, you should have seen, because this probability, the probability of 2, is less than 0, which is impossible. You can't have a negative probability. But all of the probabilities do sum to 1. So you need both properties to be a probability distribution. And then the last one, all the probabilities are between 0 and 1, but if you add all the probabilities together, you do not get 1. I think you get like 31 30 seconds, I think, if you add all those fractions together. So that is not a probability distribution. Okay? All right. So that's basically a probability distribution and how to find out if something is a probability distribution or is not a probability distribution. Now, with the probability distribution, you also have mean and standard deviation, which brings us to this. So the mean of a probability distribution, specifically of a discrete random variable, is given by mu. We still use mu, and it's the sum of x's times the probability of x's. So what we're going to do is we're going to take all the x's and we're going to multiply by all the probabilities of x's, and we are going to get a number, like whatever it is, and after we add all those together, and that's going to be our mean. Also, I note here that the mean represents a theoretical average, so it doesn't have to be an actual outcome that's possible. For example, let's say that you have a probability distribution, and it is of how many people in a household, let's say, in the United States, like the average number of people in the household. And actually, according to the last sentence, I think the average number of people per household is like 2.5 or something like that. Well, can you actually have 2.5 people in your household? And the answer is no, right? You may wish your sibling was treated as half a person, but they aren't. So 2.5 is the theoretical average of how many people are in the household, but it is not the actual, it's not a possible outcome, right? Okay, variance of a discrete random variable is given by the following formula, and we'll walk through how to calculate this. And then standard deviation, once again, is the square root of a variance. So remember, standard deviation and also variance are measures of how spread out your probability distribution is. So if you have a lot of different possible values in your probability distribution that are far apart, your standard deviation is going to be larger. If you have a more consistent value in your probability distribution, then your probability distribution is going to be smaller, and your standard deviation smaller. All right, so this is the probability distribution, the same probability distribution that was with the industrial psychologist, but notice how I added another column, and this column is for showing our work with the formula so you can see how this is calculated. So what we do is we add together all the x's times the probability of x's. So basically this column is just to show the work for multiplying across, and that's what we're going to do. So 1 times 0.16, 2 times 0.22 is 0.44, 3 times 0.28 is 0.84, 4 times 0.2 is 0.8, 5 times 0.14 is 0.7. And then according to formula, we add all these together, and when you add all of them together, you get 2.94. So that is the mean value for the industrial psychologist. Right? So the mean's not too bad, but you need the mean to figure out the standard deviation, which is a little bit harder. So the standard deviation formula, let me actually write it down here first, is the sum of, actually the square root, the sum of x minus mu quantity squared times the probability of x. So I'm going to have one column for x minus mu because that's the first thing in my parentheses. I'm going to have one column for x minus mu quantity squared, and then my last column is x minus mu quantity squared times the probability of x. You don't need all these three columns to show your work, but with that being said, I think that it helps keep your work organized. So you could do this all in one step and just go right to the last column and add all those numbers together. All right, so let's do this. So we have x minus mu. Now mu, remember, I'll write it up here again, as a reminder, is 2.94. So we'll take x, which is 1, minus 2.94 is negative 1.94. And we do this for all of them. So 2 minus 2.94 is negative 0.94. 3 minus 2.94 is 0.06. This is 1.06. This is 2.06, right? So I just took each x value and subtracted the mean. So the x value changes because it's 1, 2, 3, 4, or 5, but the mean is just the 2.94. And then my next column is to square all these values. So I'm just going to square all these values. So negative 1.94 squared is 3.764. This is 0.884. This is 0.0036. This is 0.124. I think that's rounded a little bit. And this is 4.244. And then finally, we take each of those values and multiply by the probability of x. And the probability of x changes because it's a function of x. So the probability of x is whatever is in that row. So for example, 0.16 times 3.764 is 0.602. Okay, 0.22 times 0.884 is 0.194. 0.28 times 0.0036 is rounds to 0.001. 0.20 times 1.124 is 0.225. And then finally, 0.14 times 4.244 is 0.594. Okay, and then we add all of those together, and we get 1.616. Remember that this is called the variance, but we're taking the square root to get the standard deviation. So my final answer is 1.3. And I'm only going to round to one decimal place because my data are the x values, and really my data is whole numbers. Probabilities is not the data. That's how often each data value occurs. My data is actually the x values, or the values of the random variable, which are whole numbers. And so I'm just going to round one further than what the x values are, which is 1.3. If you want to be more accurate, you can. But make sure you're accurate and carrying out at least 2, 3, 4 decimal places, depending on how accurate you're going to be in your answer. And especially when you're on Math Excel, if you do these problems, you may find that when you're doing the problems, you might get it right, but you're doing the process correctly, but when you round, you're off a little bit, and that's just because you didn't have enough decimal places when you calculated your final answer. All right, so that is mean, variance, and standard deviation of a probability distribution. So the next example on the following page, I'm not going to walk through here, but I will have the answer to, because the process is the same, and I'll show you what the answer is in the notes. So I will attach a completed version of the notes that has the columns listed with the probability. And the probability distribution is the same one about the sales calls that we did a couple pages ago. 0, 1, 2, 3, 4, 5, 6, 7. And the probabilities were 0.16, 0.19, 0.15, 0.21, 0.09, 0.10, 0.08, and 0.02. Okay, so as I said, the solution is going to be online, and you'll see the work for that. Okay, the last thing I want to talk about in this section is expected value. Expected value is a useful concept because what it is it tells you on average how often a value occurs in a probability distribution, and actually it's the same thing as the mean. It just has a slightly different interpretation. So, but numerically it's actually exactly the same. And expected value is what we would expect to happen over doing thousands of times of doing the same game or probability experiment. So actually most games have a negative expected value for the player. For example, if you buy a lottery ticket, that has a negative expected value for the player almost always. Because if you buy the lottery ticket, they're banking on you to lose, because what they do is they bank all the money in a pot, right? They pay off the winners, And then after they pay off the winners, they keep the rest of the money, right? And that's what the lottery is. And if the lottery, if it didn't have a negative expected value for the player, then the lottery wouldn't be making money and lotteries wouldn't exist. But that's why lotteries do exist. So for example, if you have a raffle, let's say, and raffles are also a similar type of thing, but usually they're for fundraisers, but really raffles are just the same thing as lotteries. So at a raffle, 1,500 tickets are sold at $2 each for 4 prizes. We have a $500, $250, $150, and $75 prize, and we buy 1 ticket. What is the expected value of your gain? So we're going to create a probability distribution. And in this probability distribution, we have to figure out, what does X represent? Well, that represents how much money what are the possible values for buying a ticket? Well, if I bought a $500 ticket, or if I bought a ticket and won $500, it'd be a $500 ticket. But we had to spend $2 to get $500, so really that's a $498 prize. If I win the $250 prize, it's really a $248 prize because I had to spend $2. And so basically we're just subtracting $2 from each prize. And then of course there's the most common result, which is what's the probability of me losing. And if I lose $2. Okay, so these are the 5 scenarios. The probability of each prize, since there's only 1 prize of each, this is just 1 out of 1,500. Now they don't always have to be 1 out of 1,500. Sometimes you might come across up with a problem where there might be like 3 $250 prizes, let's say, and then this probability would be 3 out of 1,500. But for this problem, it's just 1 out of 1,500. And then that leaves 1,496 tickets left over to be losing tickets. So notice how all my probabilities add to 1. Double check that that's right. And I subtracted $2 from each prize. And now we calculate the expected value. Well, the expected value is the sum of x times the probability of x, which is the same thing as the mean. So I'm going to take each x value. So the first x value is 498. I'm going to multiply it by the probability, 1 over 1,500. And then I'm going to add the next one, 248 times 1 over 1,500. And I'm going to add the next one, 148 times 1 over 1,500. And then I'm going to add the next one, 73 times 1 over 1,500. And then, because it's a negative, I'm going to do minus 2 times, and don't forget, this is 1,496 over 1,500. Now, you can do all this in your calculator and calculate it, but there's actually a shortcut here. They all have a denominator of 1,500, so you can factor that out. 498 times 1 is 498. 248 times 1 is 248. 148 times 1 is 148. 73 times 1 is 73. And then we still have the minus 2 times 1496. So you still have to do that. But look at how much easier that is. So do what's in the parentheses here, then divide by 1,500 at the end. Anyway, the answer is negative $1.35. So basically, for each ticket, you can expect to lose, on average, on average $1 and 35 cents. Actually, so I already said lose, it would be a double negative. So you don't want to lose a negative amount of money, you just lose a positive amount of money, right? Okay, and that's how you calculate expected value. So come up with the probability distribution first, apply the formula, and then do the math. Let's do the next one then. So try to come up with this probability distribution on your own, see if you can think of what it would look like, and then look at what I come up with. So in this problem, you're playing a game with a friend, and you're rolling a 6-sided die, and you pay $350 to play the game. After you roll the die, you earn the same number of dollars of the number rolled. So what this means is, let's say I roll a 1. Well, that means I gained $1. But if I rolled a 1 and gained $1, I still had to pay $3.50 to play the game. So if I in the end, I'm really losing $2.5 or $2.50, right? Because if I gained $1, I still paid $3.50. And we do this with every roll. So for example, if I roll a 2, I'm really losing $1.50. If I roll a 3, I'm only losing 50 cents. If I roll a 4, now I'm starting to make money. If I roll a 5, I have $1.5, and if I roll a 6, it's $2.5. And because it's a 6-sided die that we're assuming is fair, the probability of each of these rolls is 1/6. So what is my expected value? Well, you could probably guess what it is just by looking at it, but I'll write it out anyway. All of these are going to have a 1/6. So in the parentheses, we just have a negative 2.5 minus a 1.5 minus a 0.5 plus a 0.5 plus a 1.5 plus a 2.5. And after you write it all out, I think you can clearly see that this is just 0. So 1/6 times 0 is 0. And this actually has a special name. This is what we call a fair game. So a fair game has a probability or has an expected value of 0. And that means that if you play this game over time, you may lose and gain money here and there, but over time you average out to 0. So over time you will neither gain nor lose money. So you could actually play this game with a friend if you want, and over time you guys won't either lose or gain money. Now sometimes you might walk away, if you played this several times, with like $20. Sometimes you might walk away with, losing $20. But over time, that's what we're saying. Over time, you are going to have a fair game, and you won't gain or lose money. All right, and that's probability distributions for discrete in a nutshell. The last 2 sections of Chapter 4 talk about specific cases of discrete probability distributions, and that's what I'm going to talk about in the next video.